Greetings and good evening, everybody. And thank you for joining us for Cafe Sci. My name is Dan Lavoie, and I'm honored to be your host this evening. Cafe Sci is presented by PPG. Cafe Sci is also supported by the good people like you. Thank you to everyone who donated to support this program. If you are unable to donate, but you still would like to support Cafe Sci, the most helpful thing you can do is invite your friends to join the audience. Cafe Sci takes place the first Monday of each month, and you can register for next month's speaker at CaymanScienceCenter.org. It is my pleasure to introduce tonight's speakers. Our first speaker is Jerrod Crosby, PE, Chief Operating Officer at Worcester and Associates. Jerrod brings 30 years of experience in highway construction and design. A graduate of Ohio University, he oversees day-to-day operations to ensure technical quality across all design projects. Joining him is Joshua Haydo, PE PTOE, Worcester Traffic Engineering Team Lead. Josh has 20 years of experience in traffic engineering and transportation planning and holds a civil engineering degree from Virginia Tech. Tonight, Jerrod and Joshua's topic will be solving Pittsburgh traffic challenges with smarter engineering.
While we go through tonight's presentation, we're going to move through this similar to how we would move through a project. So we start with collecting the data, we start with analyzing the data, and then we get into the design. To start off the traffic impact study process, I'm going to turn it over to Josh, and then I'll be back in a few minutes to talk about the design process. So, Josh Haydo.
Thank you, Jerrod. So I am Josh Haydo, Senior Traffic Lead at Worcester and Associates. I'm going to talk about the first aspect of these projects, which I take the lead on. It's a multi-step process. What we know is traffic is everywhere. So what do we do about it? We first have to study it. So I'm going to talk a little bit about traffic studies. So first step in any sort of study, and in a traffic study as well, is identifying the scope. So that entails two major questions. What are the issues? What are the concerns? Obviously, when you think about traffic, you think about congestion. So that's measured in two different ways. Typically delay, which is, how long you're sitting, waiting, not moving, getting frustrated when you know that you should be moving. And then that's directly correlated to stacking and queuing. So, when vehicles experience excessive delay, they begin to back up. So that's not only frustrating, but it can cause safety issues when those queues block driveways, block intersections, or create, sight obstructions for other motorists on the road. And another aspect of all of our studies that kind of weaves through all of these things is, of course, safety. A couple aspects of safety are of visibility and sight distance. Being able to see other motorists on the road, whether they're approaching you, making sure they can see you when they're coming up behind you. And also, when you're turning onto a road, being able to see to your left and to your right without obstruction to make sure that, you have adequate room to merge out onto the highway safely. Speeding plays a role in that very thing, sight distance. Obviously, it's a little bit easier to merge onto a road when traffic is going 20, 25 miles an hour. When traffic's going 50 or 55 miles an hour, you obviously need to be able to see vehicles when they're much further away in order to make a safe maneuver. And we don't just necessarily trust that everyone out there is obeying the law and following the posted speed limit. We know that that's not the case. So we are always studying speed and evaluating conditions, considering the speed the traffic is actually moving rather than just assuming that they're moving at the speed limit. And then finally, we're primarily focused on vehicular traffic tonight, at least in our discussion, but pedestrians and bicycles always play a role in that as well. So that's another aspect of our studies that's always there in some cases or locations more so than others. Downtown Pittsburgh, obviously you're going to see a lot more pedestrians, a lot more bicyclists, but it's always a consideration when we are identifying the scope of the study. So 3 basic questions. What are the concerns? Where are the issues? So, is it an intersection? Is it a series of intersections? Is it a corridor? And then when do the problems occur? So this could be days of the week or time of the day. Typically, we look at peak hours, rush hours for commuting, which historically has been between 7 to 9 a.m. and 4 to 6 p.m. But different studies sometimes necessitate looking at other periods of time. We do a lot of work for schools. School arrival occurs between 7 and 9 typically, but school dismissal obviously happens, that's starting at 2:30. So we're expanding our study area or our study timeframes to make sure we capture that school traffic. Same thing, places of worship may have Sunday traffic that's its biggest peak in traffic. And then of course you have situations like here on the North Shore with 2 stadiums, the Science Center itself, a music venue, special occasions where, those things may vary from day to day, week to week, different times over the course of the year. So Jerrod briefly mentioned one of the projects we worked on. This is just kind of an example of applying those principles in the real world on a project that we did in the city. This is Penley Park South in East Liberty. You may know it as the Whole Foods at the corner of Euclid Avenue and Penn. Some challenges we faced on this project were the presence of many pedestrians, many bicyclists, and at the same time as we were doing this project, which began in 2016, the city was in the process of converting Euclid Avenue from a one-way street to a two-way street. So obviously we had to coordinate with a lot of different entities, the city of Pittsburgh, the Urban Redevelopment Authority, and others, to make sure that, when we were looking out in the future to when this development was going to open, which is the case now, that our conditions that we were analyzing are true to what is actually out there, which wasn't the situation when we began. So how do we conduct a traffic study? The first thing you need are traffic volumes, and collecting traffic volumes is as simple as you might think. You go outside and you count cars. Picture here on the lower left looks like a really boring video game. That's actually a traffic counter. When I first started at Worcester 13 years ago, one of the first things I had to do was sit on the side of the road for 2 or 3 hours at a time and count cards and press those buttons on that counter. And that's how we got our traffic data. Technology's obviously advanced even in that short amount of time. We now use cameras. So this is the computer and the screen for a camera. It's mounted on usually a utility pole or something close to an intersection. And it's up, 15, 20 feet up in the air with a bird's eye view of the intersection. That video is recorded and then reduced electronically, and we're able to have our counts without anybody being on the site except to set up and take down the camera. And going even further, now we have drone capabilities where we don't even have to set up a camera. We can have someone set a drone to hover over an intersection and do this very thing, record that video and process it in the same way, and we have traffic counts within a matter of hours. One other tool that we use, automatic traffic recorders or ATRs, you might know them as tube counters. You're ever driving down the road in your vehicle and hear thump thump? If you're anything like me, before I knew what these were, that would always cause me to slow down when I saw them or when I hit them, thinking, oh, that this is the police or the law enforcement out trying to give tickets. That's generally not the case. That's engineers like us collecting data. So these are useful because they can be set for longer periods of time, can leave these down for days, weeks, even months, and they collect not only traffic volumes, but they do identify speeds and also vehicle classifications. So when you're studying a traffic flow, it's important to differentiate and understand the composition of that traffic. Passenger cars operate differently than a delivery van or a tractor trailer. So understanding the composition of the traffic you're looking at is going to have impacts on the results of your study. So as we're looking and collecting traffic counts, we're of course obviously identifying the presence of pedestrians and cyclists, looking at speeds. And then another aspect is, so we've talked so far about traffic, the traffic and the vehicles themselves. It's also important to identify certain characteristics of the roadway network itself. So those are things such as approach grades and roadway widths, lane configurations, geometry, traffic control, be it a stop sign, a multi-way stop, traffic circle with signal, and restrictions, one-way streets, things like no turn on red. This is all information that we need to collect when we're doing a study to make sure that we're accurately modeling the study area. Couple pictures here. That's a pedestrian head. That one's actually in East Liberty. Example of a steep terrain, not at all uncommon here in Pittsburgh. Bicycle lanes. And then these last two images are examples of sight distance. So if this is taken from the perspective, you go back, this was taken from the perspective of someone sitting in the driver's seat trying to turn onto the road in front of them, and their view of oncoming traffic was obstructed by, vegetation. So sometimes those obstructions are something that can be moved, sometimes they're not. Certain areas downtown, you have buildings that are up very close to the roadway edge. Some things you just can't move. So you have to deal with things like vegetation, embankments, parked cars, all things that we look at to ensure the safety of motorists, pedestrians, and bicyclists when we're conducting our studies. So at this point in the study, we have our existing conditions. We have what traffic is like today, the condition of the study area. But when we're doing a traffic study, we're looking into the future. If we're looking at a development of some sort, things take years to develop. If it's a multi-stage residential development, that might be done in 6 phases over the course of 10 or 12 years. So we want to look all the way out to the future to make sure that we don't get everything built and find out then that we have a traffic problem. So we always assume some level of traffic growth in the future. That varies from area to area based on data that's been collected and maintained by an agency called the Southwestern Pennsylvania Commission, at least here in Pennsylvania. And we also have to take into account developments. We're typically doing studies for specific developments that are going to occur. Jerrod mentioned, convenience stores, schools, residential developments, hospitals. So we might be studying a particular project, but 2 blocks away, there may be another project that's also being proposed. So we have to project traffic for all of those developments and put that traffic on the roadway network so that we're analyzing what things are actually going to be like when all of those things are open and operational. So to identify, the number of trips that we can expect a development to generate, we turn to ITE, the Institute of Transportation Engineers. They've been collecting data for decades and continuously updating it as traffic conditions change, studying different, various land uses, different types of residential developments, retail developments, schools, hospitals, etc. And it's all compiled in this manual that, based on an example of a school, maybe by the number of students, it's possible to estimate how much traffic you can expect that new school to generate. And then lastly, we have, we know how much traffic we're anticipating in the future. Where is it coming from and where is it going to? The existing counts that we perform, or the counts of the existing intersections, are very helpful in that. Traffic can, typically follows the same patterns as it does and just builds upon itself. But we also utilize something called a gravity model. This is just a sample of the output of a gravity model. It uses census data, identifying centers of employment, centers of residences, and we use this information to model the fastest routes to a site and from a site from different directions and different points of interest to get an idea of all the traffic that's going to come to this site. X% is going to come from the north on this road versus 47% from the south on such and such road. So with all this information, we're able to have a picture of a future condition when our development is open and traffic has grown all around us. This is just another example of a gravity model with a bit more detail. You can see it can get very, very granular in terms of the distribution of traffic. Now, the modeling. So we've gathered all of our information. Now we have to plug it into a model, into modeling software. There's a couple of different options. There's many more than this, actually. We primarily use something called Synchro and SimTraffic. An alternative is HCS, and then VisSim is a more robust model. We're going to show that to you at the end of this presentation in our case study for the West End Bridge. But they all do more or less the same thing. Some have some different capabilities, and this is technology that is constantly evolving. We kind of already covered the input. That's all the information that we gather, the traffic volumes and classifications, information about the roadway, and we even have the ability to model and adjust specific driver behaviors. So in an area where drivers might be a little bit more aggressive due to congestion or other factors, all of that information can be put into the model to calibrate it, because we want our starting point or our existing condition in the model to look very much like what it is outside in the real world. And then finally, the output. The output is the answers to the question we asked on the very first slide. What is the problem? What are we looking at? It's delay, which is measured in seconds per vehicle, and stacking or queuing, those are interchangeable words. Just the number of vehicles sitting in a lane at a given time, and how likely that lane is to, or that line of traffic to exceed a certain distance. So this is a visual representation of one of our models. This is out of Synchro and SimTraffic. It's not a video game. It is real data. This is an intersection that's just outside of what was formerly the Shenango Valley Mall. It's being redeveloped right now, and we conducted the study. So all of the information behind this visualization is that data that we collected. It's real counts, it's field measurements, it's the timings for that signal and the phasing that are being modeled there are all from real data from inside the traffic controller. This is playing on a faster speed just to kind of make it not quite so slow, but this is what we look at. The visualization is exactly that, but behind that is tons and tons and tons of numbers and printouts and data, and that is a traffic study. So some really good reading material if you ever want to put yourself to sleep. But all of that analysis and all of that data and all of those numbers lead us to solutions. So we identify impacts, we identify deficiencies, problems. Jerrod, my colleague, is going to come back up and talk a little bit more about how we implement those in the real world. The traffic study looks at these things operationally and says, how are they going to work? We're looking at models, but Jerrod puts pen to paper and is going to talk a little bit about how these are designed and ultimately constructed.
Thanks, Josh. What you see up here are the three most common types of roadway improvements that we design and we implement for solutions. Traffic impact study goes through and tells us exactly what we need to design and implement in the field. It could be one of these, it could be two of them, it could be all three of them, it could be a combination of any. At this point in a typical project, we're about 6 months into the process. With the traffic study approval and everything identified, we now enter into the design phase where we start putting the plans together using CAD softwares, meeting all of the criteria books for everything we have. There's criteria for signing, there's criteria for pavement, there's criteria for pavement markings. There's probably about 100 books that would stack about this high. As we do our designs, we have local, federal, and state oversight. So everything that we design has to go through. Generally, PennDOT is our most popular. So we go through PennDOT, we go through DOMI, or we go through municipal review. So there are checks and balances to ensure that wherever we are and whatever we're doing, that's being reviewed and approved by the local authorities. So um, turning lanes, that's the first one I'm going to get into, is Josh talked about with capacity. If you've ever been driving on a single lane highway where you only have one lane, obviously you're stuck. If you're sitting at a light, you're 4 cars back, you want to turn right, you got to wait for the light. If you install a right turning lane for something like that, that obviously gives you more capacity. You're now able to go past the traffic that's waiting, make your right turn, and be on your way. Um, Sometimes it's a simple solution like that, a single turning lane. Sometimes it's a left turn lane, a right turn lane, but we get into dual left turns and dual right turns, which things get a little bit more complicated on the highway. This is a project we did in Cranberry Township. This is 228 right off of 79. This is coming up on the left. That roadway wasn't there. The project that we had was the commercial development on the left. That actually leads back to the UPMC Penguin practice facility. On the right used to be Westinghouse, then Console. Not quite sure if it's either of those right now, but that had about 1 million square feet of office in it. So you can imagine at 5 o'clock, this intersection had a ton of traffic, and we were adding to it with the commercial development. So in order to make that work, what we identified in the traffic impact study was very much outside the box. You can see on the top portion of the screen, we installed, on the bottom portion of the screen, we have dual lefts. On the top portion of the screen, we installed triple lefts. And we had to design that and make the traffic signal work that those two movements could work simultaneously. When we brought that solution to Cranberry Township and PennDOT, they thought we were a little bit crazy because it's never been done in the state. So we went through and we put the plans together. We proved that it worked. We had to get creative with our design, but still meet criteria, make sure we're safe, make sure everything functions. And this is kind of what that looked like on paper. So this is a single plan sheet. The whole plan set out of this was probably 200, 250 pages, a lot like that, but bigger. So you can see a lot of detail goes into this with our softwares that we have, with surveying modeling and our Civil 3D software, which is a CAD software. We actually create a 3-dimensional model of everything that you see on the screen that can get sent to the contractor. They can go out and build everything from that plan. So one of the, oh, sorry, wrong way. One of the issues that we have with intersections like this, which it's not going. There you go. Is the size. As Josh said, in the city of Pittsburgh, we have topography issues. We have steep grades. We have rivers. We have bridges. We have buildings right up against the roadway. A lot of things that limit us in installing roadway improvements that are this large, just due to constrictions. This intersection took up roughly over half an acre of asphalt. So if you try to put that down in an intersection in the city of Pittsburgh, obviously you'd have to knock down buildings to do it. So that, if that's the case and we identify that early, we go to the next phase, which is roundabouts. These are becoming a lot more common. Some of you might have driven through them, some of you might not have, but we look at these now anytime that we might warrant a traffic signal as an alternative to it. The reason we look at these as an alternative and why they're becoming more popular is safety. When you install the previous mentioned turning lanes, a left turn, whether it's signalized or unsignalized, is the most dangerous maneuver you can make because you're actually pulling out in front of possible opposing traffic. Usually those movements, the opposing traffic might be going 40, 50 miles an hour. If there is a crash, that's what we refer to as an angular crash. They're usually high speed. They're the most severe crashes that we have, and they lead to the most fatalities. So with a roundabout, you eliminate all the left turns. So you increase the factor of safety on a roundabout tremendously. You don't decrease the amount of accidents, but you increase the safety by decreasing the severity of the accident. There's still, I don't know if you saw in that video, people still don't really understand how to use these quite yet. So there are side swipes and fender benders, the same amount of accidents, but the severity of them is completely lowered and there's no fatalities. Another piece of safety that happens here, because it's a large circle, um, we reduce the speed limit for the approach grades coming in. So traffic that might have been going, push the wrong button twice. Let's go back. Traffic that might have been approaching from this side was going 45 miles an hour. We reduced that speed to 25. So now we're dropping the speeds. We're making sure that we have lines of sight for pedestrians that can see the cars. Cars can see the pedestrians. You can see the whole way through this so that everyone can see what's coming, which is another safety improvement for everyone coming through. The problem with this, from the sidewalk and the grading for it over here, the circle itself is 160 feet. The whole project takes up, it's more than 250 feet across. So the reason it's that big is 79 is up here, Route 19 is down here, and this project was a large mixed-use commercial project. So we have a lot of a grocer and a lot of commercial, fast food, a lot of residential, but we had to get large delivery vehicles through here, semi-trailers. So the red in the middle is what we call a truck apron. Truck is supposed to come around here just where the passenger cars go, but when that trailer off tracks as that's making the turn, because they make really wide turns, says so right on the back, that trailer will track through here but not get hung up on anything. But in order to do that, we need a lot of space. Again, this intersection was more than a half acre. All of the folks on the corners were happy with the project, so we were able to obtain the necessary rights of way. We had the room to do it. But again, you put this in an urban area or you put it in a city, we can't move buildings to make some of these work. So unfortunately, sometimes we have to forego those safety upgrades just because we can't make it fit. In some cases, this is a plan of what that looks like. Again, similar to the other one, this was probably 150 pages of plan sheets, have the model for everything underneath. We can look at that model and actually see where a drop of water will flow so that we can drain the road properly. Tons of technology and engineering goes into creating what you saw on the screen. So an alternative to that roundabout is what we call an urban or mini roundabout. This is much smaller. It's only 70 feet across. This is the Northway Mall in Ross Township. They approached us, as you can see, oh man, I keep pushing the wrong button. They had a very odd configuration as their entrance. So they brought it to us and tasked us with helping solve some driver confusion with an ugly intersection. So the solution we came up with is the mini roundabout, and it works great. Same safety improvements, same capacities, everything functions well, but something like this, you can't get delivery vehicles through. So we can make them smaller. They work for passenger cars, they work for bicyclists, they work for pedestrians. But if you're in an urban corridor and you need deliveries, commercial projects, they just don't work. So again, the size of these is a limiting factor for us, which takes us, well, this is the plan for that one. As you can see, we have to lay out all the pavement markings, label everything. There's criteria for everything that you see on this screen. Even the size of the text on a sign is known to us. So that's what that one looked like on paper. When these don't work, it leads us to the most versatile thing that we have, which is traffic signal. That's where the technology portion of what we do comes in. It gives us a lot of options on how to connect things together, which we're going to demonstrate later with the case study for the West End Bridge. Signals have been around for a while. The first one was in London in 1868. It was actually a gas light signal. I'm still not sure how that worked, but The first electric signal here in the US, 1914 in Cleveland. Then our first signal here in Pittsburgh, 1924. So 101 years of signals. They have come a long way. This is what they used to look like. Little boxes with lights in them. Some of them had someone controlling the box. Some of them had a pre-timed controller on it. But you can see how far we've come. A pre-timed controller, the original signals were just a stand in the middle of the road, and it was on a timer, similar to a lamp in your living room that comes on at 11 o'clock. But that timer would turn and change the lights from the main line to the side street every 30, every 60 seconds. That technology, unfortunately, is still in place in some of these. Even though we have new technology, new signals, everything looks good, you might run into a pre-timed traffic signal. If you've ever been sitting at a light and there's no traffic and you're sitting at a red light and you're waiting and you're waiting and waiting, you're at a pre-timed signal or something's broken. But what happened in the 1960s is they developed what is called a volume density traffic controller. So that just means that they created detectors, which I'm about to get into, which are able to count the cars, know where they're coming from, know if they're coming on the side street, if they're making a left, if they're making a right. And that's able to tell the software in the traffic signal controller who needs to get a green light and for how long. So the way that is made possible is through detectors. If you've ever seen this shape cut in the pavement or this shape cut in the pavement, that is what we call a loop detector. There's two types. There's presence detection. That's usually the shape you see here, which is right up at the signal, right at the stop bar. These things are 40 feet long. So if you're within 40 feet of that stop bar and someone's honking at you that you need to pull up to activate the signal, they're wrong. That's not a thing. These are advanced detectors. So these are placed usually, depends on speed, but they're usually 250 to 300 feet away from the stop bar. So as soon as you get on the main line and you're 300 feet from that signal, it knows you're there. The way these work, and they've been in place for a long time, this shape, you actually run just a metal wire through it, loop it around a couple times. That goes back to the traffic signal controller. You put an electric charge on it, and it becomes an electromagnetic field. That's sitting in the pavement. If your car goes over it, a large metal item disrupts that magnetic field, and it sends a signal, what we call a call, to the traffic signal controller, and that says the signal controller knows it's there, and then that begins to count the cars and know what is happening. It can count, it gives more and more green time with the more and more cars that are there. If that comes up and that's in the left turn lane, it now knows there's someone in the left turn lane. It'll give that phase of the traffic signal a green light, and once it clears, it flips back. Usually we set the controllers to go back to what we call mainline green to give time to the main line where most of the traffic is. So technology has taken us from these cuts in the pavement, which can be problematic. Anytime you do roadway improvements, if you have to overlay or widen the roadway, these get ripped up and they have to be reinstalled. So as we progressed, this is a video detector. If you've ever looked up and saw this, it's not a security camera. It's not recording you. It's just it's not even really a live feed unless someone's looking into the software in the controller, which I'll get into that a little bit later. But these work very similar, except they're a video camera, so they're focused on the roadway. And when there's no traffic, there's nothing moving, the pixels aren't disturbed. As a car approaches, the pixels get disturbed, and these begin to count those cars. They know where they are. They do the same thing. They send the calls back to the signal controller, and they begin to add up the time that we need for the green light to try to get the entire platoon of traffic through in one phase. This technology, not only does it now see it, it's up on the mast arm or on the signal, it's out of the roadway. You don't have to replace it if you repave it. But this, as Josh stated, can collect data. So not only is it determining the phasing of the traffic signal, but it's also storing that data in the traffic signal controller itself, which then, if we were given permission, we're able to get real-time data 24/7, which helps us put things into the models and give us a better idea of what's happening. To take a look at what this looks like, if you hooked a laptop up to the traffic signal controller that had a video camera, this is what you would see. You can see the yellow all the way up at the top of the screen. That's when the camera picks the car up and it knows what's happening. The green at the top is the advanced detection, so it knows it's coming. And then as this car approaches, this will light up. He'll stay green because he has to wait. This will go green, but then it'll disappear. That now tells the signal controller it's passed. So it counted it, but now it knows to release that call so it doesn't change the timing of the traffic signal. So this is same thing at night. This is the same thing in winter. This guy on the left, don't ever do what he's about to do. It's a bad idea. Don't do that. So in all types of weather, these work, and they give us a lot of tools to do things that we'll talk about a little bit later in the presentation. This is another detector. If you've seen this, this is what we call a radar detector. Functions very, very similar to a video detector, but it doesn't have the video portion of it. It's just sending out a radar signal, and that signal is bouncing back. When it bounces back, same thing. It knows where the cars are. It knows what to do with them. It tells the traffic signal what to do. So with all of that data, now that it's stored in the signals themselves continue to get more technologically advanced. And some things that we can do, instead of a signal being an intersection by itself, if you drive through a commercial corridor, when signals act by themselves and they're not talking to each other, you might start at a green light, you go 200 feet, and you stop at a red light. So what we do in those cases, now with some technologies we have, we're able to coordinate them. Now, you could coordinate 5 signals, 2 signals, 20 signals, it doesn't matter. There's a lot of systems locally that are doing that to have a better and safer flow of traffic. The original coordination was called time-based. Basically, we would take the traffic impact studies, we would program the different times of day for your AM, your PM peak, your Saturdays at 12, and then we would connect all of those signals. We'd program maybe 10 of them, and then we'd set the clock inside of them to a certain time, and then they would change all at the same time, depending on the time of day. Sometimes the clocks don't run right. They get a little bit off. Sometimes the traffic patterns might change. Things like COVID clearly changed the traffic patterns that we have. And Tuesdays are different than Fridays, so you're kind of stuck with that programming. Something like this, we can connect those signals directly with a fiber optic line or through an Ethernet radio, which is similar to like a Wi-Fi. So now those signals are able to talk to each other in real time. The detectors are collecting the data, storing that data, and it's sending it from this signal to the next signal saying, there's 100 cars coming, get a lot more green. And then that signal passes that information on and on and on. So this gives us a lot of powerful tools to, in a commercial corridor, really keep traffic moving. That leads us to intelligent transportation systems. Now that the signals have all this technology on it, we're able to monitor that. What we have on this side, this is just a command center. This is a technician sitting in front of screens looking at those live feeds from the detectors, whether they're video feeds, they're looking at the data, the timings, the backups, the queuing, and they're able to make adjustments in real time, which is great. Now we don't have to rely on the signal to do it or timing to do it. We actually have eyes on that 24/7 that are changing things. You might recognize these. We call those changeable message signs. In relation to this, they're able to alert drivers. If you're, say you're traveling on the Parkway, you've seen the sign 19 minutes to the airport. If there's a crash, you might see a sign that says an hour and a half to the airport. Find a different route or seek an alternative route. So by monitoring all these things and tying all these technologies together, we're really able to function and focus on the safety of the road and not only keeping people safe, but getting them from point A to point B much, much faster, which we are going to demonstrate how we take all of this and we put it together and we use the more detailed models, the more detailed data that we're able to collect, and the technology that's either in place on most traffic signals, or we can install it to come up with a solution to the very, very congested areas that might not be able to be widened. You can't widen a bridge. You have to knock it down and put up a new one. So to walk you through our case study of what we found here at the West End Circle, I'm going to turn everything back over to Josh to finish this off.
Thank you. Thank you again, Jerrod. Okay, so here we are back at the West End Bridge. Again, chosen for a variety of reasons. It's familiar to us, as being new residents to the North Shore. We know that this is right outside. And anybody here travel the West End Bridge or the West End Circle on a somewhat regular basis? Great, perfect. So treated this very much like a typical study. I apologize, for boring you earlier, giving you kind of the background, but hopefully that kind of helps demonstrate what we went through and the process behind this, so that you can better see and appreciate what we're doing here. A couple images here of the circle. This is the south end of the West End Bridge. So we chose to do, as I mentioned, when we do a traffic study, we look at often multiple different time periods, AM, PM, maybe a Saturday. For the purpose of this demonstration, we chose to do the afternoon peak. It's one that we're very familiar with, and it actually just occurred here only a couple of hours ago today. So again, you see southbound traffic crossing the West End Bridge, or trying to. And another big holdup, if you travel through here, this is 65, trying to turn left onto the bridge, and not being able to. If you're ever sitting in this line of traffic, it's kind of sad because of this grade. You can see the light turning green up here, but nobody moving, because only on every other cycle does this traffic move so that this traffic can make their left turns. So you can see that situation happening right here. If this traffic was to get the green light, they wouldn't be able to go anyway, because the holdup is actually at the other end of the West End Bridge, which is causing stacking all the way back and beyond the north side. So just briefly, our study area, I told you we look at, we identify the intersections in question, the culprits in this case, two on either end of the bridge, all of which are signalized, operating somewhat independently of one another, not really connected, as Jerrod was just talking about, that interconnectivity with the signals talking to one another. So we went out, we collected our data, we did counts, all the stuff we talked about, got field conditions, built our model, calibrated our model. We ran it a couple times, looked at it, being very familiar with conditions in the afternoon in this area. We were able to say, well, that doesn't look right. Traffic on 65 backs up way longer than what the model was showing. So it took some calibration, but we got into a place where our existing condition was matching very, very closely what we experience in real life from day to day. So what these pictures illustrate along the top are three pictures that show the three major phases of the intersection at the far end of the West End Bridge. We focused, after looking at the model and running some analysis, we focused on this particular intersection as having a major opportunity to improve traffic within the whole corridor. So these diagrams just simply show, during the three phases of the traffic signal, what movements are allowed to move and which movements are stopped. So the three graphics below show the changes that we made. So there's not a very drastic change here or even here. Not very drastic changes at all. You can almost, not even see what's different. But what I do want to call attention to is the fact that under existing conditions, southbound west end bridge, which is what gets congested in the afternoon, is only free flowing during one of these three phases. You can see in these other two phases it stopped. Whereas after the changes that we analyzed, two of those three phases, that traffic is allowed to continue moving. And only in the third is it stopped to yield to other movements. So this is just simply back up there. This is the same simulation that I showed you before from the Shenango Valley Mall. Data is all the same. It's all the same information. It's not quite of a robust model as the one I'm about to show you. I mentioned it briefly earlier when I talked about the different models that are available to us. The last one was something called Vism. And again, it's far more robust, and you're going to see that immediately when I show you what that model looks like. So this is not a video. This is built the same way as the model you saw previously. Those cars are in a model. Those are based on the counts that we performed, the field measurements, the calibration, etc. So this is the existing condition at this end of the West End Bridge. You can see the stacking along, southbound across the bridge. Eventually it starts to pick up and these queues will clear. But during all this time, you see traffic continue to back up. It even goes off the screen and off the model on 65 trying to turn left onto the West End Bridge. And it's also backing up further into the north side. So here's some of our results. We identified that even though we only made a change at one intersection, West Carson, so the West End Circle at the far end of the bridge, we saw dramatic impacts at both ends of the bridge. So what this table shows, I know it's a lot of information. Basically, it's just simply all of the approaches to this intersection, to each of these intersections, all of the lanes that compose each of those movements. And we talked about delay. It's measured in seconds per vehicle. So this is existing versus what we modeled as a potential solution. These are corresponding letter grades. LOS stands for level of service. It's just a way to simplify and categorize and rate the amount of delay that you're experiencing. It's just like a report card, A, B, C, D, E, and F. So under existing conditions, we got some really bad grades here. Someone's in trouble. We got a lot of Fs, a lot of Es. With the changes, there's still quite a few failing movements. You see a lot more Ds, Bs, even some As. Remember, this is the West End Bridge. It's always going to have some issues. But the most important column here is on the end. It's the difference. So there are a couple situations here indicated by the red dots that show delay actually gets a little bit worse with what we're proposing. There's a finite amount of capacity out there. The changes we made, bear in mind, we're not expanding or building lanes. We're confined to the same amount of capacity. We really just have to push it around, and sometimes pushing it to the proper movements that need the most attention, if you do it thoughtfully, utilizing this software and this technology, it can make a big difference. So that's evident in the fact that you can see how many movements experienced an improvement, and they are substantial. This table is just simplified. It doesn't go into each individual lane. It's just all of the movements or all of the approaches at those same signals. And what I want to highlight here is the global, or what is the overall improvement at each of these intersections. So at the Circle, the West End Bridge and Carson Street, 52% reduction in delay. So imagine if you're someone who goes through that intersection daily, however much time it's taking you right now, Imagine it taking half that much time. And even though this is the only intersection where we modified the timings and the phasing and did any sort of modification to what is there today, it had a drastic impact on the other end of the bridge, the Route 65 off ramp. Globally, we reduced congestion or delay by 82%. The other metric we use that I mentioned early on in the presentation is stacking. So this graph represents 95th percentile queue. That's what we present in our reports as kind of a worst case scenario. We want to plan for not just the average, but, cover ourselves for 95% of the time. We want to have storage lanes and things of that nature that are long enough to accommodate the stacking. Looking at some of these numbers, I'm going to highlight this one because this is the West End Bridge southbound or going away from the Science Center towards the West End. That queue is almost 2,400 feet. That's almost half a mile under existing conditions. And you can see across the board, the red is existing, the green is with our modifications. Still have some excessive queuing here, but by and large, we're improving or reducing those queues across the board. In some cases, very, very drastically. So this is another critical one, the off ramp from 65, which was the one that backs up for so long. Because the West End Bridge is moving so much better, you're no longer getting through only on every other cycle, you're getting through on every cycle. A very similar graph, this is the median, as I mentioned. We don't typically use it for analysis, but this is over the course of that entire 2 hours. So that 95th percentile was the very worst of the worst within that 2-hour period. You can see, the results are just far more drastic, far more exaggerated. These reductions are far more significant when you look at not just simply the very worst 15 minutes within that 2-hour time frame, but that entire afternoon peak. So again, the West End Bridge, 2,100 feet, that's the equivalent of about 85 vehicles, reduced to 620 feet, which is the equivalent of 25 vehicles. So significant reduction. So now graphs and charts and tables are all great. This is the same simulation I chose just a couple of moments ago. This is our calibrated model of the West End Bridge today. And it doesn't take an expert to see when I flip over to what it could potentially look like with these changes in place. Drastically different for the better. No more queues across the bridge, no more stack up on 65. Now, as this goes on and over the course of an hour, 2 hours, this will build. But this is kind of an apples to apples comparison of what we saw in the previous model. So it is demonstrative of the power of this model and of these tools and of this technology to make improvements without any physical infrastructure being added. So I do want to say that this is not a fully engineered solution. We did this as a case study simply to demonstrate, the power of these tools and of this technology. But it certainly does paint a picture of the capabilities that we have. So we've talked a lot tonight about the past and the present, and this really kind of is the future. And we wanted to present you with an example of something that hopefully you've experienced, and maybe this gives you a little bit of hope about your future commutes in the future. So I know we talked an awful lot. Hopefully it wasn't too boring. We want to leave some time for questions. We love answering questions. So happy to answer questions about anything that I or Jerrod presented tonight, or even just general questions relating to traffic that popped in your mind this evening or throughout your day today. So
we're going to be having someone in the audience. So if you raise your hand, we'll come to you with a question. We also have some questions online. So every 1 or 2 questions, we're going to switch to online. So if you have a question in the audience, go ahead and raise your hand. We'll try to get to you.
Thank you for great presentation. Western Circle, did that last Tuesday. Because my son said, I got to be at the airport by 8 o'clock for an international flight. Said, can you pick me up at 5 from Millvale? And then last Monday, he said, hey, I looked and the tunnels are really backing up by 5 o'clock to go out the parkway. Can you pick me up at 4? Did that. 28 was already backing up. Looked at Waze. It said, hey, go 65 to the West End Circle. Stop there for a couple lights on 65 before turning onto the bridge. It then, instead of going straight there, sent me, back roads from the circle there and stuff. So I wondered, obviously, that's not the typical thing, but do you take into account the once in a while thing like, oh, the tunnels are really clogged up and your traffic coming onto 65 is going to be 30 or 50% higher? Do you get into that level of modeling, or is that beyond your 95th percentile that you don't worry about it?
I would say that's primarily captured. We have a number of levels of safety or factors of safety in our analysis, and that's one of them. In a city of this size, with the restrictions, obviously, one major thoroughfare being blocked or congested for some reason really pushes the problem to a lot of different places. So, to the best we can, we do capture that, but there are some things that you just can't quite plan for. Sometimes bridges fall down.
Not the ones I do.
Yeah. No.
I had a question. When did that change get implemented? Because I've actually changed my driving pattern at that intersection because of that. I used to wait on 65 back, or on the 65 exit ramp back onto 65. And I thought it was dangerous. So I stopped going that way and hooking on through the main road, I think is what it was labeled. So I was kind of interested, one, do you guys think about the induced demand of the changing patterns that like as they exist, people using alternative routes versus going back to the 65, which is the quickest way if there's no traffic, or and just wondering when this was implemented, so if I should start taking that exit ramp again.
Well, this was done as a case study. So this wasn't a fully engineered project done for anyone. We just analyzed it for the purposes to demonstrate the technology for this evening. It is something that now that we have it, we would certainly like to market it to the city and to PennDOT to get it implemented. So to answer your first question, it's not implemented yet. It might be in the future. We'd love to make this happen, because again, we're right in. Let me turn this thing on. We're right in the area, so it impacts us every day. But you are correct, and that's part of the solutions that we have to provide when we do open this up to traffic. This will become an alternate route. Other people might begin to use it, but that'll take pressure off of some of the other areas, such as the merge between the Fort Pitt tunnel and the bridge. It's a mess too. So by improving any routes, especially a main corridor like that, you can take congestion off of other highly congested area, making it better for everybody, no matter where they're going.
Yeah,
the airport fast.
Things will tend to balance themselves out. When I leave the office, I have one of two choices. I either take Fort Pitt or West End. So depending on how traffic is, depending on what time of day it is. So yes, obviously, if this were to ever happen, this simple model is not taking into account, well, it's going to draw additional traffic from other areas. It would, but then as Jerrod said, it dilutes traffic in other places. There's only so much capacity in the city, but you can see, just even with all that traffic that's in the West End today, just pushing it around a little bit and giving priority to certain movements, you can really get a lot more cars through a lot faster. So it is creating capacity. Other people are likely to utilize that capacity, but that's only going to open up other corridors.
All right. So online, we have some questions here as well. We'll get to a few of these. Bill asked a two-part question in our chat for the virtual stream. What impacts traffic signal coordination for two-way roads? How do you make it work both ways? Does AI help? And the follow-up to that is, are there any creative solutions to changing daily traffic conditions? Which you guys are saying.
Yeah, for all of the studies, we look at every approach, as Josh showed through this case study. When they go through their numbers, we're looking at the left turns, the through movements in all directions simultaneously. So for two-way traffic, for certain phases in the traffic signal, we might have different timings on different approaches, and we're able to program the software to do that. And then through the coordinated systems, AI, I mean, obviously, we demonstrated that connecting these and with the ever evolving technology, it gets the data faster. It gets us more data to be able to put better timings into it. And I'm sure, you have a number of technologies that we don't even know what they're going to be that will only better the situation.
Yeah, it's already all moving so fast. The advancements from, you saw gaslit signals to, and how far it's come. It's going so fast. Yeah, there's a lot we don't know in a year. How much more could come along, but this is at the forefront, and it's exciting stuff.
Yeah, from the 60s to the early 2010s, not much of this was available. So this is just technology really ramping up and giving us all of these new opportunities to get you from A to B safer and faster.
Thank you. You mentioned the smart sensors that you have at various intersections. How sensitive are they to bicycles? Because I find myself sitting there watching, waiting until a car pulls up behind me.
A lot of the sensors, the technology is getting better. They do have difficulties picking up motorcycles and bicyclists in lanes, simply due to the size. The video detectors probably being the best because of the movement. So that technology still needs to happen. We do actuate like pedestrian push buttons, depending on where we have, if we have bike lanes or if we have shared paths to come to a signal. There's actually, instead of just pedestrian actuation, there's now actuation for bicyclists from the lane. So if you're in that bike lane, you can actually push the button if the technology's available. But some of the things that you're out there, some of the signals, I mean, they've been there a while. If they don't have the new technology, you're not getting that benefit. So.
All right, we have a question online from Kathy. How come the moving traffic circle wouldn't work at the West End Bridge? I thought that was an idea that was considered at one time.
What was the question?
She asked, how come the moving traffic circle wouldn't work at the West End Bridge? I thought that was an idea considered at one time.
It was a circle. They removed it. What they had to do is add, instead of, if we can.
Do we have an image in there of that?
Where's that side? In the middle photo right here, this was never there. So when you came to the West End Bridge 15 years ago, this was just a giant traffic circle. So you would have to circulate around to get to 51. They went underneath the train trestle, and they got rid of most of the circle to allow this movement to free flow. So it was there. It didn't work great because you have the intersection of four major highways happening. So with what we proposed in this, that would allow this movement to do what it was designed to do, which is keep that traffic flowing off of the West End Bridge and open everything else up.
Hi, I have a question about left turn lanes. Convention for many years was at an intersection, when the traffic would allow people to make a left turn, they were the first ones to be allowed to turn left. But I've noticed a change over the years where at many intersections, the left turn lane is held until the straight through traffic is predominantly run through the intersection. And that's like a change in convention. that I was wondering, is there a significant improvement in the flow because of that?
Well, I will start, and Jared, if I miss anything, you piggyback. So a lot of signals are now equipped to make that determination of whether or not to put the left arrow first or at the end. Because what happens is when you have so much through traffic, and an example that I can think of off the top of my head, because I was in that area for a long time, is McKnight Road. You have so much traffic on McKnight Road, you might have a 200-foot left turn lane, but there's so much through traffic that it continuously blocks out that left turn lane. So the through lanes fill up, you might only get 1 or 2 or 3 cars in that left turn lane. It doesn't make sense to give them all that green time at the beginning. You let the through traffic go first. Within that platoon of through traffic, all the people that want to get into that left turn lane fill up that lane. You do it at the end. So it all has to do with how much through traffic is on the road. You just want to you want to fill up that turn lane as much as you can before it gets blocked, before you dedicate a lot of time to it. Is that
Right.
fairly accurate?
And it's referred to as a lagging left because it's behind. So we can study that. We can look at that as an opportunity, as an option to, again, like Josh said, keep the flow of traffic moving is best we can.
So your case study, this didn't involve any kind of physical changes. So it was really the timing of your lights and things like that.
Correct.
So how long, I guess the question is really how often would a study like that need to be done to make sure that, you have this, you implement it for 3 months, and then do you do again? How long do the case studies take to do, and how often would things like that be implemented to really maximize benefit?
Well, the case study was something that we did Worcester purely for the something to present here. We weren't contracted by anyone to do that. That's just something we wanted to have, something that people here could relate to, hopefully, and see. So it would have to be coordinated with a number of different agencies. Get PennDOT on board, accept our study, and something of this.
I mean, the real study to implement this and get it approved would take roughly a year to go through everything. Now that we have some of the data collected and some of these things built, we could speed that process for this particular project. But yeah, our projects, nothing moves real fast. From the time a client says go, we're at least 12 to 18 months before we have approvals and they start construction. Smaller projects obviously go faster. Larger projects take a little bit longer. But yeah, we didn't have to. I mean, the other answer to your question, I guess, how long would this last with ever changing traffic patterns? That gets back into the ITS, the Intelligent Transportation System. With technologies that could be added to this, you could connect this system and put it to a command center, and you could have someone watching it and updating it in real time. So that way, when the Steeler game gets let out, you can have someone sitting there and making sure you have the proper flow of traffic. And I think one of the questions on there with AI, I'm sure that's going to just continue to advance, that it can modify and change on its own.
We have 2 questions from our chat, both about roundabouts. So I'm going to get to each of them. We'll start with one here from Gina asked, were roundabouts originally invented as a safety feature? Or did they have another original intention when first designed? Also, thank you for your fascinating presentation.
Thank you. I don't know. I don't know why they were originally invented. I mean, obviously they are very, very popular in Europe and have always been there. They didn't get popularized here. I mean, in my first part of my career, if you said the word roundabout in Pennsylvania, you got looked at like you had 3 heads. So it wasn't until 20 years ago that these became more of an option. And what I can say is they're great when it comes to safety. I mean, it's a massive safety improvement. And if we could put them everywhere, we would.
The second question we have from Virginia is regarding roundabouts. If a car is on the inner circle, it seems there might be confusion about who has the right of way when the car wants to exit the circle. Is there anything you could add to that to help kind of clarify that kind of thing?
Yeah, the round, everything that we showed you tonight is a single lane roundabout. Um, which just has one lane of traffic. There is no inside and outside because multiple lane roundabouts, if anyone's seen the vacation movies, you just can't get left, Big Ben Parliament. They are much more difficult to navigate. And for the same purposes that we have to make the circle real big, when you have a multi-lane roundabout with a truck, that circle goes from 160 feet to 400 or 500 feet because now that truck has to maintain completely in his lane because it can't track over without being a safety issue. So
Hi. Um, I heard that those little buttons that you hit to like cross the street to like change the light. Some people say that those buttons don't actually do anything and they're just like a placebo effect. They're there to like,
um, they do. They if they're working, they do. What we found, oddly, is only 5% of people push those buttons. So most people are just standing there waiting for a gap in traffic. But if you push it, it calls what we call a pedestrian phase. Those phases need to cross with certain phases of traffic to make sure that we're not sticking a pedestrian out in the middle of the road while someone's turning left, which would be a safety issue. So sometimes they take a while for that call to go through and line up with traffic so that you can get the pedestrian walk. So yeah, you want to when you have a pedestrian crossing, you want to cross with the parallel to the same set of traffic. So you have to wait until the main line phase is going this way so that you could cross this same pedestrian crossing so that you're not putting them into an opposing situation for safety.
A particular pedestrian phase will come up. I mean, it's called a signal cycle because it is cyclical. It goes in a certain order. And so a particular pedestrian phase comes up at a certain point of time if it's called with the traffic that's moving. So if you press that button, it's not going to turn all the traffic lights red and have you go straight across. If you just miss that moment in the cycle, it may take a while to get through the rest of those phases to get back to the appropriate time for that crossing. So that's why sometimes it can take a long time, particularly if you basically just missed your opportunity. It does continue to go through that entire cycle so that you're crossing at the appropriate time when traffic is moving parallel with you.
We have a couple questions building up online. I want to get through a few of those quickly here. And one of them was from Timothy. It was interesting. He said, you talked about how Command Center is used to look at lots of cameras to create message board messages across town. Do you think there is potential for AI to help manage creation of these types of messages based on incoming data? Or will this kind of message creation always need a human being to analyze and interpret what's out there?
I think AI is changing everything so quickly that I think the capabilities there are voluminous and terrifying in some cases. But yeah, I'm sure as that technology continues to rapidly grow, AI can do a lot of that.
And this one, I think, is going to be one that's going to be on a lot of people's minds. This is from an anonymous person in our audience here. Tunnels. Nothing is more infuriating than 5 mph entering a tunnel during traffic slowdown that only emerge with no traffic, and you can drive as fast as the speed limit. Can brighter lights in the tunnel and a surface that does not reflect brake lights inside the tunnel elevate unnecessary slowdowns? Are there any other solutions to help tunnel slowdowns?
Wider tunnels would be necessary. Some of the things that impact our tunnels, which don't get as much recognition as the fear of people driving in. We can't change driver behavior, but some of the things that impact the tunnels are the interchanges just prior to. I mean, the weave from the Duquesne Bridge to the Fort Pitt Bridge, and people trying to get over 3 and 4 lanes as they approach is a problem. The intersection right before the Squirrel Hill Tunnel that takes you up into Homestead is problematic. There's 2 merging movements. There's off ramps, there's on ramps, and then you have the same thing on the other side of the Fort Pitt as you come down to what looks like a bowl of spaghetti at all of those ramps to going to 19 and everywhere. So those things all kind of couple together, that they were designed for a lot less traffic. And now that Pittsburgh has grown and grown, some of those problems, they just need to be tore down and redone. I mean, a third lane through the tunnel would fix a lot of problems, but there's a lot of mountain above it.
Some of that's driver behavior that may or may not ever change. I come through the Fort Pitt tunnel every day on the way in, and I know that once I get out of the tunnel, I want to go 2 lanes to the left to get to the North Shore, and that lane is always backed up forever. You wait and you wait and wait, knowing every day that as soon as you get out the other end, you have all the time in the world to get over 1, 2, 3, 4 lanes, but yet people are never going to seemingly, learn that lesson and take the right lane and get in there much sooner. That lane will continuously back up. And again, you emerge the other side with tons and tons of capacity. And I don't know what can change that except driver experience.
And knowing these things makes it even more frustrating to drive through that.
Yeah.
First of all, thank you so much for the presentation. I had no idea this much even went into things like that. My question is, I know that in certain situations, emergency services need to get through heavy traffic to get to different emergency areas and things of that nature. Is that something like that route, something that you guys consider whenever you go through simulations like this, or is that just a special case scenario?
Yes, I mean, there's a number of things that we do and we're able to provide. One of the things that are required on some larger roads are wider shoulders, just for that reason. Certain routes are designated as national highway safety routes, so you're required to have a 10-foot shoulder so an emergency vehicle can get through. I didn't touch on it, but some things that we have with a traffic signal is called emergency vehicle preemption. You've seen, they look like little speakers, old megaphones up there. That's actually an audio detector, so that if a vehicle is coming through with a siren, whether it's fire, whether it's an ambulance, whether it's police, that picks it up, it triggers the call to the controller, stops all the other traffic, and allows them to come through. So we put that piece of software on almost every signal that we do.
So following up on the lagging left, I've noticed that a lot to go from green at the beginning. So if it's a left turn beginning, it goes to green and then it'll go to a flashing yellow, which I think is much better than it just going to red. So is that a recent thing or am I just noticing it?
Well, there's 2 aspects here. So there's something called a permitted left turn, where you'll get a left turn arrow, and then that goes to a red ball, meaning once you lose that arrow, you have to stop. And that can be for a number of reasons. That's can be because there's so much traffic that's going to be coming at you in the other direction that it's just not safe to try to make that maneuver. You may go from a green arrow to a green ball, which has now become from a green arrow to a flashing yellow arrow, which means you can continue to proceed with caution. Traffic coming the other way is moving and it still has the right of way. I think it's the Department of Transportation has decided that they too feel that the flashing yellow arrow is a little more clear to motorists, indicating that yes, you continue to go, but you have to proceed with caution and give the right of way to the approaching vehicles.
And that's the new policy. So anytime we design a new signal, that's what we're installing. The issue with going out and trying to retrofit existing signals, that head has to be further out another 8 feet. So if you have a mast arm signal, they're simply not long enough to be able to do it. You have to replace the whole thing, so it becomes costly. But everything new, you'll see the flashing yellow.
Okay, and then a totally different one. So in Cranberry, you mentioned that 2 lanes going to the left to go to the Lemieux Center. And a couple years ago, they opened up the tunnel underneath, which is really neat for that. And now I hear they're going to put a Wegmans behind there, which I think is going to have a few more cars coming in there. And the exit from that Lemieux Center seems to be just 1 or 2 lanes coming out there. Have you guys been hired to do that follow-up study? Because man, I think that's going to be a disaster.
Not yet, but we were actually a little smarter than that. We, if I could find the photo, when we knew that this was going to turn into a lot more development. So I don't know if we have a video of it, but we actually graded it and pushed all the sidewalks and any poles and utilities further off so that coming out of the UPMC facility, should they need more capacity, we allowed the room for it. So I believe we allowed for 2 future lanes to come through there. So if it's Wegmans that creates that need, I hope they give us a call. And we can certainly install that for them.
I want to quickly go through a few questions we have online. The questions keep coming in. I know we just have a few minutes left. I want to try quickly to get to a few of these. Joseph asks, how accurate are those simulation results compared to the real world results?
Very, very accurate. Like I said, it's a number of factors, not just, the cars, the vehicles themselves. We look at classifications, we look at speeds, restrictions, things as tiny as, the roadway widths. Vehicles travel slower and have to on narrow lanes as opposed to wide lanes. We do the approach grades because vehicles that are stopped take a longer time to accelerate when they're, on an upgrade. So yeah, they are very accurate. It's based on a methodology. We used to have to do it by hand when I was in college. That's all built into the software now. It's been refined and updated over the years. But we do, as I mentioned with the West End Circle, we also go out and we calibrate. We observe the traffic, we model it, we go back and check, hey, does this existing condition look like what it looks like in the real world? Because there's no sense projecting beyond that if our existing condition isn't modeled correctly.
And we've taken another step on that. We sometimes on larger projects prepare an after study. So we go out and verify that what we thought was going to happen is indeed happening. So
another question here from Emily quickly is, what human or societal changes have impacted your field during the time you've been working in it? And if the field has adapted to it, and how? In the case, what I'm trying to ask isn't clear. An example might be something like more people tailgating, Google Maps / Waze directing people to alternative routes when there are backups, driver assist, etc.
What was the first part?
The first question was, what human or societal changes have impacted your field during the time you've been working?
It's in everyone's pocket. That's the worst thing that we have is our cell phones.
Yeah.
I mean, those Google Maps, those Waze, even though it's getting you where you're going, some people are holding it in their hand. Texting distracted drivers, that would be the biggest thing that creates more issues than we can put these solutions in, but because of that, we have more issues out there, which is why there's a new PA law that says, don't do that. They'll pull you over. You'll get a ticket.
One last question online. We had a few comments on there. A couple people thanking you as well as good luck for your future endeavors. The one question more for Joseph is, how do you think the future connected vehicle technology will change roadway design?
Well, we've actually had a few software demonstrations and actually have some softwares that the connected vehicles are giving us a lot of information. So through that connected software, we're able to get more and more in-depth data to further verify the gravity models.
Right.
And a number of things. And eventually these softwares are out here, and I don't know much about it, but for autonomous vehicles to log in and talk to the traffic signal, that signal will be able to tell your car 20 years from now. I don't know how that software works, that there's a red light coming, and it'll help you stop, which will increase safety. So technology is going to, well, hopefully I don't have to deal with too much of it. I don't have more than 15 more years. So it's going to pass me by.
We have time for one, maybe two questions at most.
All right. In New Jersey, one of the very common traffic management things is the jug handle, the left turn from the right lane. You don't see that in Pennsylvania. Is that a difference between New Jersey DOT and PennDOT, or is there advantages and disadvantages that don't work in the Pittsburgh area, or what?
They take up space just like everything else. So our topography, railroad tracks, rivers, a number of things, but they are in use. If you go through 22 on Murraysville, I actually was part of the design project way back when we did that. Everything's a jug handle. What I showed on the video at 228 PennDOT's redoing 228 from 79 all the way to Route 8. They are taking all the intersections out and they're putting in jug handles and signalizing those. So on large scale projects, we love to use it because again, it gets that traffic out of the way and doesn't impact the flow of traffic. So it's a safety upgrade, less rear ends, and less left turns, which I touched on are the worst. So they're there. We just, these rivers and bridges get in our way a lot.
But as you travel the country though, you see different things in different
Yeah.
states. We work primarily here, but we have jobs in other states, and you know, some of it is just that's the way it is there, and you know, maybe they'll catch on elsewhere, but
Right.
you know, folks do things a little bit different in Texas. It's a different set of circumstances, different set of criteria. May or may not affect us in someday, but and again, maybe it will.
All right. In closing, do either of you guys have anything you'd like to talk about as the last about 1 minute, or any kind of closing statements you'd like to hit on?
No, I think we're just demonstrating, and it sounds like a lot of the questions are kind of showing what the evolving technology is able to do for us as engineers, and to get you guys, you know, home from here quicker and safer. So
Yeah, and it's a field that I've grown to really love. I think it's fascinating. I hoped coming into this, is very happy to be asked to do this. I hope it was interesting to others. You know, everyone's experienced it in one way or another. Maybe the nuts and bolts are a lot more than you ever needed to know. I know I can't drive down the road without thinking about everything that I'm seeing. It's a little bit of a torturous situation, but I don't know. I love what I do, and it's pretty fascinating to see how fast it's moving, how fast it's moved in the past 10 years, 20 years, and who knows with AI and everything else, and just how fast everything is moving, what's to come a couple years down the road.
Well, as the Cayman Science Center, I'd like to thank Jerrod and Joshua for being here, as well as Worcester and Associates. It's been an excellent talk. And thank you to our audience for being here this evening. I'd like to close out with a round of applause for our speakers.
Thank you.